there is a number that quietly governs every story ever told about existence. 13.8 billion years. If that number is wrong, then every timeline in cosmology shifts. The first stars, the first galaxies, the formation of black holes billions of times more massive than the Sun, even the window in which life could emerge, all of it depends on that single measurement. In 2013, the European Space Agency's Planck satellite delivered what many physicists considered a definitive answer. By mapping the cosmic microwave background, radiation released just 380,000 years after the Big Bang, Planck reconstructed the universe's expansion history with extraordinary precision. The age it derived was 13.797 billion years, with an uncertainty of less than 1%. In statistical language, the model fit the data at overwhelming confidence. To appreciate the scale of that precision, consider this. Reducing the uncertainty to under 1% is equivalent to determining the age of Earth to within only a few tens of millions of years, out of billions. In cosmology, that level of agreement is rare. It signaled maturity, stability, closure. That number became structural. Supercomputer simulations that track dark matter across cosmic time were calibrated to it. Predictions for when the Milky Way assembled were anchored to it. Estimates of when the first heavy elements formed, carbon, oxygen, iron, depended on it. If 13.8 billion years is correct, then galaxy formation follows a compressed, tightly scheduled evolution. But measuring the age of the universe is not like counting tree rings. We do not observe time directly. We observe light. Light stretched by expansion. Light whose wavelength shifts toward red as space grows. We measure that redshift, translate it into distance, then translate distance into time. Each translation depends on how we believe space has expanded over billions of years. Change the expansion history and the clock changes with it. Over the last decade, that clock has begun to show strain. Independent measurements of the universe's expansion rate refuse to agree. Local observations of exploding stars imply one value. The cosmic microwave background implies another. The discrepancy approaches statistical significance levels that physicists describe in sigma, high enough that chance becomes increasingly improbable. A few kilometers per second per megaparsec may sound trivial. In cosmology, it can mean billions of years. Then, in December 2021, a new observatory unfolded nearly 1 million miles from Earth. Its purpose was simple: look deeper into the early universe than any telescope before it. It was expected to confirm the established timeline. Instead, it began to expose structures that appear older than the schedule allows. And when structures mature faster than physics permits, one possibility rises above all others. The universe may have had more time than we thought. In 1929, a quiet revolution began with a shift of light. Edwin Hubble, working at the Mount Wilson Observatory in California, measured the spectra of distant galaxies and noticed something unsettling. The spectral lines, the chemical fingerprints of hydrogen and other elements, were displaced toward red wavelengths. The farther the galaxy, the greater the shift. It was not random, it followed a pattern. Galaxies were not simply scattered through space, they were receding from us. And more profoundly, space itself was expanding. This discovery transformed cosmology from philosophy into measurable science. If the universe is expanding today, then in the past it must have been smaller, denser, hotter. Run the expansion backward far enough, and all structure converges toward an initial state. The concept of the Big Bang was born not from speculation, but from spectroscopic measurement. From that moment, the expansion rate became the master key to cosmic time. Astronomers defined a constant to describe it, the Hubble constant, the speed at which galaxies recede per unit distance. Measure that rate precisely, and you can calculate how long the expansion has been underway. In principle, it is simple. In practice, it has proven one of the most difficult measurements in modern astronomy. For decades, estimates varied wildly. Early calculations suggested the universe might be as young as 7 billion years, or as old as 20 billion. The uncertainty was not philosophical, it was instrumental. Measuring cosmic distance requires layered techniques: parallax, Cepheid variable stars, type 1, a supernovae. Each step in the distance ladder compounds error. By the late 1990s, New observations of Type 1 supernovae introduced an unexpected twist. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, discovered that distant supernovae were dimmer than predicted. The universe was not slowing its expansion under gravity, it was accelerating. This result, confirmed at greater than 5 sigma statistical confidence, implied the existence of dark energy, a component driving space apart faster over time. The expansion history was no longer linear. It curved. In the 2000s and 2010s, increasingly precise measurements narrowed the Hubble constant. Observations using Cepheid variables and supernovae in nearby galaxies consistently yielded values around 73 km per second per megaparsec. Meanwhile, analysis of the cosmic microwave background by the Planck collaboration in 2013 implied a lower value, about 67 km per second per megaparsec. The difference is roughly 10%. On paper, it is small. In cosmic chronology, it translates into billions of years of difference in inferred age. This discrepancy, now known as the Hubble tension, has grown more statistically significant as measurements improved, approaching levels that make random fluctuation increasingly unlikely. Multiple independent methods confirm each side. Calibration errors have been hunted aggressively. None fully resolve the gap. If the local universe expands faster than the early universe model predicts, something in our cosmological framework is incomplete. Either unknown physics influences expansion at late times, or our interpretation of early universe signals is subtly biased. The stakes are enormous. The expansion rate does not merely tell us how fast galaxies move, it determines how we convert redshift into time, how we assign ages to distant galaxies, how we define when cosmic dawn occurred. If the expansion rate is mischaracterized, then the cosmic clock derived from it may also be miscalibrated. For nearly a century, redshift has been treated as the ruler of the universe. But what if that ruler is slightly warped? To understand that possibility, we must examine the oldest observable light, the radiation that locked in the universe's earliest measurable state, and the assumptions hidden within its interpretation. There is light in the universe that has been travelling for nearly its entire history. It does not come from a star. It does not come from a galaxy. It comes from a time before either existed. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, detected a faint microwave signal that seemed to arrive from every direction in the sky. At first, they suspected interference, equipment noise, atmospheric disturbance, even pigeon droppings inside the antenna. But the signal would not disappear. It was uniform, persistent, cosmic. What they had found was the afterglow of the early universe. Radiation released when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, space was opaque, a dense plasma scattering light endlessly. Afterward, photons could travel freely. Those photons still move through space today, stretched by expansion into microwaves. This relic radiation became known as the cosmic microwave background. By the late 20th century, satellites such as COBE and UMAP revealed that this background was not perfectly smooth. It contained tiny temperature fluctuations, variations of about 1 part in 100,000. These minute differences represented density variations in the early universe, the seeds from which galaxies would eventually grow. Then, in 2013, the European Space Agency's Planck satellite delivered the most detailed map ever made of this ancient light. The precision was extraordinary. Planck measured temperature differences across the sky with micro-Kelvin sensitivity, allowing cosmologists to fit theoretical models to the data with remarkable accuracy. From that fit came the age, 13.797 billion years. The agreement between model and measurement was so tight that many considered the debate over cosmic age effectively closed. The lambda CDM model, incorporating dark matter and dark energy, matched the pattern of fluctuations with stunning fidelity. Statistical residuals were minimal, confidence levels were high, but the cosmic microwave background does not measure age directly. It measures patterns, acoustic oscillations frozen into radiation. Converting those patterns into a number for cosmic age requires assumptions: how fast the universe expanded, how matter and radiation interacted, whether the laws of physics were constant over time. change the expansion history and the inferred age changes, change the interaction rates of particles in the early plasma, and the scale of fluctuation shifts. The microwave background is often described as cosmology's gold standard, and yet, like any standard, it rests on a framework. If that framework is incomplete, the conclusions derived from it must be reconsidered. Subtle anomalies in the data, as cold spot, unexpected alignments on large angular scales, remain statistically modest, but persistent. They do not overthrow the model. They whisper that perfection may be an illusion. If the universe is older than 13.8 billion years, the evidence must still pass through this ancient light. Any alternative timeline must reproduce its delicate pattern with equal or greater precision. The question is no longer whether the cosmic microwave background is correct. The question is whether we are interpreting it through the only possible lens. To probe that uncertainty, astronomers would need a new kind of observation, one capable of looking beyond the microwave afterglow and into the era when the first galaxies ignited. In December 2021, that instrument began its journey. On December 25, 2021, while most of Earth slept, a telescope the size of a tennis court unfolded 1 million miles away. The James Webb Space Telescope did not launch to rewrite cosmology, it launched to refine it. Positioned at the Sun-Earth L2 point, its gold-coated mirror segments and cryogenically cooled instruments were designed to capture infrared light stretched across billions of years of cosmic expansion. Where previous telescopes saw darkness, Webb would see structure. Where Hubble reached its limits, Webb would continue. Its mission was clear: look back to cosmic dawn, roughly 500 to 800 million years after the Big Bang, and observe the first galaxies taking shape. According to the established timeline, those galaxies should have been small, chaotic, chemically primitive. They should have contained perhaps tens of millions of stars, fragile systems only beginning to assemble under dark matter's gravitational framework. In July 2022, Webb released its first deep field images. Within days, astronomers analysing data from its near-infrared camera identified something unexpected: bright, compact sources with extreme redshifts. Spectroscopic follow-up suggested some of these objects existed less than 600 million years after the Big Bang. But they did not resemble infant galaxies. Preliminary mass estimates indicated tens of billions of stars. Some showed evidence of organised structure, density profiles more consistent with mature systems than turbulent beginnings. Their brightness implied stellar populations far larger than simulations predicted for that epoch. At first, caution dominated the response. Photometric redshifts can be misleading. Active galactic nuclei can inflate luminosity. Early data requires verification. Yet as more observations accumulated through 2022 and 2023, the pattern persisted. Independent teams using Webb's spectroscopic instruments confirmed multiple high redshift galaxies with unexpectedly large stellar masses. These were not isolated anomalies. They formed a population. Under the standard 13.8 billion year framework, galaxies at redshift 10 should not have had sufficient time to assemble such mass through hierarchical mergers and regulated star formation. The physical processes that govern gas cooling, star birth, and supernova feedback impose natural timescales. Compress them too tightly, and the equations strain. If the measurements were correct, then either early star formation was dramatically more efficient than current physics allows, or the galaxies were not as young as the timeline implied. The stakes escalated quickly, because Webb was not merely observing distant objects, it was testing the schedule written into every cosmological simulation. If massive galaxies truly existed so early, then the age derived from redshift might be systematically misinterpreted. The discovery did not yet overturn the model, but it did something more unsettling. It exposed a crack between observation and expectation, a crack wide enough to force a question cosmologists had not seriously entertained in decades. What if cosmic dawn was not as early as we thought? In Part 5, we examine the most extreme of these early structures, the galaxies that came to be known as the Red Monsters. Some galaxies were not merely early, they were enormous. In 2023, an international team analysing data from the James Webb Space Telescope's early release surveys reported 3 galaxies that defied expectation. Detected at redshifts corresponding to less than 1 billion years after the Big Bang, these systems possess stellar masses approaching that of the modern Milky Way. They were quickly nicknamed the Red Monsters. The name was not poetic exaggeration. In Webb's infrared images they glowed deep crimson, their light stretched by cosmic expansion. Spectroscopic measurements confirmed their distances with increasing confidence. These were not foreground contaminants, they belonged to cosmic dawn. Under the standard 13.8 billion year timeline, this presented a serious problem. Galaxy formation follows physical constraints. Dark matter halos grow hierarchically, merging over hundreds of millions of years. Gas falls inward, cools, and forms stars. But star formation is inefficient. In present-day galaxies, only about 20% of available gas converts into stars before stellar winds, and supernova explosions heat and expel the rest. The red monsters implied efficiencies of 40 to 60%. Such values strain feedback physics. Massive stars explode violently within a few million years. Their energy should disrupt further collapse. To sustain rapid growth without self-destruction requires conditions not currently reproduced in simulations. Researchers proposed alternatives. Perhaps the stellar populations were dominated by unusually massive stars, temporarily inflating luminosity and exaggerating mass estimates. Perhaps accreting supermassive black holes contributed additional light. Detailed spectral analysis has explored both possibilities, yet even conservative revisions leave these galaxies exceptionally massive for their inferred age. The issue is not a single anomaly. Webb has identified multiple high redshift galaxies with unexpectedly high stellar masses. Independent teams, using separate analysis pipelines, continue to report similar results. The statistical weight grows. If these galaxies truly existed when the universe was only 600 or 700 million years old, then structure formation occurred at a pace that challenges standard cosmology. Either star formation in the early universe operated under radically different physical conditions, or the redshift to time conversion is systematically misinterpreting how early we are looking. The stakes extend beyond galaxy morphology. Because if cosmic dawn produced mature, massive systems far earlier than predicted, then the assumed age of the universe constrains them too tightly. The timeline becomes compressed beyond what gravitational dynamics and nuclear physics comfortably allow. The red monsters do not violate physical law, they violate expectation, and when expectation repeatedly fails under improved measurement, the possibility arises that the framework itself is incomplete. If galaxies appear too mature for their assigned age, another possibility emerges, that the assigned age is too small. 200 light-years from Earth, a star moves through our galaxy at nearly 800,000 miles per hour. It looks ordinary through a telescope, faint, pale, unremarkable. But its age has unsettled cosmology for more than 2 decades. Catalogued as HD 140283, and often called the Methuselah star, this object became the centre of quiet scientific tension in the early 2000s. Spectroscopic analysis revealed something striking. Its metallicity, the fraction of elements heavier than hydrogen and helium, is roughly 1/250th that of our Sun. In astrophysics, low metallicity is a signature of extreme antiquity. The early universe contained almost no heavy elements. Carbon, oxygen, iron, all were forged later inside stars and dispersed by supernova explosions. A star with so little metal must have formed very close to the beginning of cosmic history. The problem emerged when astronomers calculated how close. In 2000, data from the Hipparcos satellite suggested an age approaching 16 billion years. That exceeded the accepted age of the universe itself. The result triggered immediate scrutiny. Distance measurements were refined. Stellar evolution models were updated. Observational uncertainties were reanalyzed. In 2013, using the Hubble Space Telescope's fine guidance sensors, astronomers improved the parallax measurement 5-fold. The revised age estimate 14.5 billion years, with an uncertainty of plus or minus 800 million years. Technically, the lower bound overlapped with 13.8 billion years. But the central value remained uncomfortable. Stellar ages are derived from precise modelling of nuclear fusion rates, luminosity, temperature, and chemical composition. These models are anchored in well-tested physics. While uncertainties exist, they are not arbitrary. Small shifts in assumed parameters cannot easily erase billions of years, and Methuselah is not alone. Globular clusters, dense spherical collections of ancient stars orbiting the Milky Way, routinely produce age estimates between 12 and 13.5 billion years. That leaves a narrow window between the Big Bang and the formation of fully assembled stellar populations. Under a 13.8 billion year timeline, the universe must cool, form the first generation of stars, enrich space with heavier elements, and then assemble long-lived second-generation stars, all within a few 100 million years. The schedule is possible, but it is tight. When distant galaxies appear too mature and nearby stars appear too old, independent lines of evidence begin to converge. Neither observation alone overturns the model. Together, they narrow the margin for error. If the universe is indeed 13.8 billion years old, then stellar evolution must fit precisely within that boundary. If it is older, even by several billion years, the tension dissolves naturally. The question becomes unavoidable. Are we observing anomalies at the edge of measurement precision, or are these ancient stars quietly pointing toward a deeper cosmic history? To answer that, we must examine the invisible framework beneath all galaxies, the dark matter scaffolding that governs how structure grows across time. 85% of the matter in the universe is invisible. It does not shine, it does not absorb light, it does not interact with atoms the way ordinary matter does. Yet without it, galaxies would not exist. Dark matter forms the gravitational scaffolding of the cosmos. Long before stars ignited, minute density fluctuations in dark matter began to grow under their own gravity. In the standard cosmological model, this process began shortly after the Big Bang. Over hundreds of millions of years, small clumps merged into larger halos. Gas fell into those halos, cooled, and formed the first stars. This is known as hierarchical structure formation. It is not instantaneous. It follows calculable timescales determined by gravity, orbital dynamics, and the rate at which matter can collapse without overheating. Numerical simulations, refined over decades and validated against present-day galaxy distributions, reproduce this growth with impressive accuracy within a 13.8 billion year universe. But when those same simulations are run backward to the first billion years, tension appears. Under standard parameters, dark matter halos massive enough to host Milky Way-scale galaxies should not fully assemble until billions of years after the Big Bang. Early halos are expected to be small, perhaps containing the mass of a few million suns. Building something 1,000 times larger requires repeated mergers, each governed by orbital decay and gravitational interaction. These processes have minimum durations. They cannot be compressed arbitrarily without altering the underlying physics, yet James Webb observations indicate galaxies with stellar masses of tens of billions of suns existing less than a billion years after cosmic origin. For such galaxies to form within the accepted timeline, dark matter halos must grow faster, merge more efficiently, and retain gas despite energetic stellar feedback. Some theorists have proposed modifications. Perhaps dark matter in the early universe behaved differently, warmer, more interactive, capable of clumping more rapidly. Others explore altered feedback prescriptions, reducing the impact of supernova-driven gas expulsion. But each adjustment introduces new complications. Changes to dark matter properties ripple into predictions for the cosmic microwave background and large-scale structure. So far, the standard dark matter framework explains those observations remarkably well. The dilemma becomes clear. Either structure formation operated under unknown physical conditions during cosmic dawn, or the time available for structure formation has been underestimated. If the universe were significantly older than 13.8 billion years, dark matter would not need exotic behavior. Halos would have additional billions of years to merge, deepen, and accumulate mass through ordinary gravitational processes. The equations would not change. The timeline would. Dark matter does not protest. It follows gravity faithfully. But the galaxies we observe may be telling us that gravity has been at work longer than we assumed. To examine that possibility, we must confront a proposal that challenges a century of interpretation. A proposal suggesting that redshift itself may not mean exactly what we think it means. For nearly 100 years, cosmology has relied on a single interpretation. Redshift equals expansion. When light from distant galaxies stretches toward longer wavelengths, we attribute it to space itself expanding. Measure that stretching, convert it into distance, convert distance into time, and the age of the universe emerges. But in 2023, a controversial paper published in the monthly notices of the Royal Astronomical Society proposed a radical possibility. What if redshift is not caused by expansion alone? Rajendra Gupta, a physicist at the University of Ottawa, introduced a hybrid model combining conventional cosmic expansion with a modified version of an older idea known as tired light. Originally proposed in 1929 by Fritz Zwicky, tired light suggested that photons might gradually lose energy as they travel vast cosmic distances, shifting toward red without requiring all of that shift to be caused by expanding space. The original tired light theory was largely dismissed decades ago because it failed to explain time dilation in distant supernova and other observational tests. But Gupta did not revive it in isolation. Instead, he proposed that a small additional energy loss component could exist alongside expansion. If even a fraction of observed redshift arises from photon energy loss rather than pure expansion, then the inferred distances of the most remote galaxies are overestimated. And if distances are overestimated, then the ages assigned to those galaxies are underestimated. Under Gupta's calculations, incorporating this hybrid redshift mechanism, alongside evolving physical constants, extends the age of the universe to approximately 26.7 billion years, nearly double the accepted value. The implications are profound. Galaxies observed at redshift 10 would not be forming 500 million years after the beginning, but perhaps 1 or 2 billion years later. Dark matter halos would have additional time to merge. Star formation would proceed under known physics without requiring extreme efficiencies. The red monsters would no longer be anomalies compressed into an impossible epoch. Gupta's model does not ignore established observations. It attempts to fit supernova data and cosmic microwave background measurements, while subtly recalibrating the redshift to time relationship. Supporters argue that the model resolves multiple independent tensions simultaneously: early massive galaxies, stellar age paradoxes, and elements of the Hubble tension. Critics respond that any modification must reproduce the extraordinary precision of Planck's cosmic microwave background results and the observed time dilation of distant supernovae without introducing fine-tuned parameters. The debate is ongoing. No consensus has formed. But the significance of the proposal lies not in immediate acceptance. It lies in the fact that redshift, the ruler by which we measure cosmic time, may not be as singular in meaning as once believed. If redshift contains additional physics, then every inferred epoch in cosmic history must be recalculated. And if the universe is older than 13.8 billion years, then the story of chemical enrichment, the creation of the elements that make planets and life possible, must also be reconsidered. Every atom of carbon in your body was forged inside a star. Every atom of iron in your blood was created in a stellar explosion. The universe began with almost nothing but hydrogen and helium. No oxygen, no silicon, no gold. The heavy elements that make planets, oceans, and biology possible had to be manufactured over time. That process leaves a record. Astronomers call it metallicity, the fraction of elements heavier than helium contained within a star or galaxy. Because each generation of stars enriches surrounding gas through supernova explosions, metallicity functions as a chemical clock. The older the universe becomes, the richer in heavy elements it grows. In the standard 13.8 billion year framework, the first stars, known as Population 3, formed from pristine hydrogen and helium perhaps 100 to 200 million years after the Big Bang. They were massive and short-lived, exploding quickly and seeding space with the first heavy elements. Population 2 stars formed next, containing small but measurable metal fractions. Only after multiple generations did galaxies reach metallicities comparable to our Sun. This enrichment requires time. Nuclear fusion rates are fixed by physics. Massive stars live for only a few million years before exploding. Lower mass stars endure for billions. Each cycle of formation and explosion proceeds at calculable speeds, yet observations from the James Webb Space Telescope have identified galaxies at high redshift, already exhibiting substantial metal content, in some cases approaching 1/10 solar metallicity. within what would be only 500 to 700 million years after cosmic origin under the standard timeline. Producing that level of enrichment requires several generations of massive stars forming, evolving, and exploding in rapid succession. The margin for delay disappears. Closer to home, extremely metal-poor halo stars in the Milky Way display complex abundance patterns that suggest enrichment by more than a single primordial supernova. Their chemistry indicates multiple stellar ancestors, a layered history compressed into a narrow early window. Globular clusters reinforce the message. Their stars share consistent metallicities, implying formation from gas that had already undergone enrichment. Dating those clusters places them roughly 12 to 13.5 billion years in age, under a 13.8 billion year universe. Only a few hundred million years separate the Big Bang from chemically evolved stellar systems. Possible, but strained. If the universe were older, even by several billion years, the chemical enrichment curve relaxes naturally. Multiple stellar generations unfold without requiring extreme star formation efficiencies. Metallicity rises gradually rather than explosively. The chemistry of stars does not argue loudly. It accumulates quietly, element by element. But when distant galaxies appear chemically mature and nearby ancient stars carry signatures of complex ancestry, the implication is subtle yet persistent. The processes that build heavy elements may have been unfolding longer than the accepted timeline allows. If structure, stellar age, and chemical enrichment all point toward compressed time, then the final question remains unavoidable. What does an older universe mean for the emergence of complexity itself, for galaxies, for planets, for life? If the universe is older than we believe, then we are living in a very different cosmos than the one described in our textbooks. Not a universe 13.8 billion years into its evolution, but perhaps one more than 26 billion years deep. That difference is not cosmetic. It reshapes every major chapter of cosmic history, from the formation of the first galaxies to the emergence of planetary systems capable of sustaining life. In 2023, Rajendra Gupta proposed a model that extended the age of the universe to approximately 26.7 billion years by re-examining how redshift is interpreted and allowing for subtle modifications in cosmic physics. The proposal remains debated and far from accepted consensus, yet its significance lies in what it accomplishes. Within this extended framework, several persistent tensions ease simultaneously. Massive galaxies observed by the James Webb Space Telescope no longer appear to have formed impossibly fast. Dark matter halos gain the additional time required to assemble through ordinary gravitational mergers. Ancient stars cease hovering at the boundary of paradox. Chemical enrichment unfolds across broader epochs, instead of being compressed into a narrow, frantic beginning. If such a timeline were confirmed, the implications would reach far beyond technical cosmology. The Milky Way would represent the product of a deeper gravitational history, shaped over tens of billions of years rather than compressed into a tightly constrained schedule. The first rocky planets could have formed far earlier than current models suggest. Habitable environments may have existed billions of years before Earth itself coalesced 4.6 billion years ago. The Drake equation, which estimates the number of technological civilizations, depends critically on time. Extend the available cosmic history, and the window for biological evolution expands dramatically. In a 26 billion year universe, civilizations elsewhere could predate humanity not by millions of years, but by billions. Yet scientific caution remains essential. The Planck satellite's measurements of the cosmic microwave background stand among the most precise datasets in all of physics. Type 1. A supernova observations confirm cosmic acceleration at high statistical confidence. Any extended age model must reproduce these pillars without weakening their extraordinary agreement with observation. Cosmology advances not through isolated anomalies, but through convergence across independent evidence. Expansion rates, background radiation, stellar physics, gravitational lensing, and galaxy surveys. What has changed is not the data, but the tension within it. High-precision observations from Webb, persistent discrepancies in expansion measurements, and the chemical and chronological signatures of ancient stars have reopened a question once thought settled. How long has the universe truly existed? If future evidence demonstrates that cosmic history stretches far beyond 13.8 billion years, then our perspective shifts profoundly. We would not inhabit a relatively young cosmos still assembling its larger structures. We would occupy a universe already deep into maturity, a universe whose earliest chapters unfolded long before our solar system formed, and whose future may extend far beyond our current imagination. The greatest revelation may not be that the universe is older, but that our sense of its scale in time has only just begun to expand.